Hey everyone, and welcome. Today, we're diving into a challenge that's totally hidden but absolutely essential to our modern world: heat. How in the world do you deal with the massive amount of waste heat that comes off of high-powered electronics? So, first things first, you can have the most advanced, most efficient machine on the planet, but nothing's perfect. And when you're messing with huge amounts of electricity, even the tiniest little inefficiency creates a really, really dangerous byproduct: a shocking amount of heat. To get a sense of the scale here, just get this. A 1 megawatt industrial drive, that's a million watts. That's 97% efficient, which sounds amazing, right? But it still wastes that last 3% as pure heat. And that adds up to 30 kilowatts of raw thermal energy that has to go somewhere. 30 kilowatts, that's a big number, but it doesn't really mean much on its own. So what are we really talking about? How can you even picture that much heat? Okay, imagine that. 20 of those little space heaters, all cranked up to max, and you stuff them all inside a tiny closet and shut the door. That is the kind of intense, scorching heat we have to manage. If you don't get that heat out and fast, the electronics will literally cook themselves to death in minutes. So, how do engineers fight back against this thermal beast? Well, it turns out there are three main ways to do it. We're going to break down each one: the classic air cooling, the high-tech liquid cooling, and these super tough sealed systems that use heat exchangers. Let's kick things off with the one you've probably seen before: air cooling. You know, if you've ever walked past a big industrial cabinet and heard all those fans whirring away, yeah, this is what's happening. Now, not all air cooling is created equal. You've got the standard method, which is super simple. It just sucks in air from the room and blows it over everything. But that can be a total disaster if the air is dusty or dirty. So a much smarter way is what's called segregated, or back-channel cooling. It basically creates a special sealed-off wind tunnel just for the hottest components, which keeps all that dust and gunk away from the sensitive electronics. All right, next up, liquid cooling. This is the high-performance option, the one you turn to when you need to get rid of a ton of heat, but you have very, very little space to do it. You know, the concept here is actually something you're probably very familiar with. It works almost exactly like the radiator in your car. There's a special coolant, usually a water glycol mix, that gets pumped through these sealed plates that are bolted right onto the hottest parts. The liquid just soaks up the heat and carries it far away to be dealt with somewhere else. So, when do you use this? Well, it's the go-to solution for the really big jobs. We're talking drives over 500 kilowatts. Or in those situations where you physically just can't fit a giant air-cooled cabinet. And that brings us to our third contender: sealed systems. This is the heavy-duty rugged option. It's designed to work perfectly in the absolute worst, dirtiest, grimiest conditions you can possibly imagine. But wait, how do you cool something if it's completely sealed off? Well, with this really clever device called an air-to-air heat exchanger. Here's how it works. Inside the box, a fan blows the hot internal air against one side of the exchanger. On the outside, another fan blows the cooler room air against the other side. The heat just passes right through the metal, but the dirty outside air never ever gets inside. It's pretty brilliant. Okay, so we've met our three cooling champions. Now for the fun part. Let's put them head to head and see how they really stack up, because this is all about picking the right tool for the job. All right, this table basically tells the whole story. Air cooling, it's the cheapest and simplest by far, but it takes up a ton of room and is terrible in 30 places. Liquid cooling is the absolute star when it comes to saving space, and it handles harsh conditions great, but it's the most expensive and complex with all those pumps and pipes. And then you have sealed systems, kind of the perfect middle ground on cost and complexity, and just like liquid cooling, they are fantastic when the environment is your main enemy. So you see the trade-off, right? It's always a balance between cost, size, and toughness. Okay, enough with the theory. Now that we get the trade-offs, let's look at where you actually find these systems out in the wild. This is where it all comes together. So first step, picture a giant cargo ship or an oil rig out in the middle of the ocean. Why on earth would they pick the most expensive and complicated option: liquid cooling? Well, it comes down to two really simple reasons. First, that salty sea air is incredibly corrosive. It would just eat an air-cooled system for breakfast. And second, space on a ship or a rig is maybe the most valuable thing they have. The tiny footprint of a liquid-cooled system is a game changer. Okay, how about another one? What about a place that's just ridiculously dusty, like a cement plant or a mine? Why are sealed systems the champs in that environment?
Because in these places, the air itself is the enemy. That dust isn't just messy. It can be conductive, causing short circuits, or abrasive, literally sandblasting the delicate components. A regular fan would just be sucking all that destruction right into the machine. Sealing the whole thing up is the only way it can survive.
So for our last one, why is plain old air cooling so common? Why do we see it everywhere in places like a clean factory floor or a city water pumping station?
It really just comes down to the right balance. If you're in a clean, climate-controlled room and you've got plenty of space, air cooling is the perfect choice. It gets the job done reliably and it is way, way cheaper. Why spend a fortune on a complex system if you just don't need to? And this brings us to what might be the single most important takeaway from all of this. For any engineer designing one of these systems, everything, and I mean everything, starts with one number you find on the manufacturer's datasheet: heat dissipation in kilowatts. You have to know exactly how much heat you're up against before you can do anything else. That one number decides everything: the size of the room, the AC you'll need, and ultimately which of these cooling strategies you're going to use. So, behind every massive, powerful machine, there's an equally powerful and usually invisible solution working hard to keep it from melting down. It really makes you wonder, doesn't it? What other amazing, invisible engineering is out there, quietly and brilliantly making our world work every single day? Thanks for digging into this with me.